Okay, still doing oscillations, and now instead of looking at a pendulum, we're looking at a spring. So we want to differentiate this equation up here. So differentiate for non-calculus people is finding the slope. And I'm hoping from the last worksheet that for non-calculus people, I kind of did it for the non-calculus people, is that you found out that the slope of a cosine graph is negative sine. And the slope of a negative sine graph is negative cosine, which means the slope of sine is cosine. So that's how they're kind of related. Also, the slope of something times, let's say we're trying to find, let's say we had a graph of x as a function of time and it's equal to 3t. The slope of 3t is just 3, okay? So we're going to be finding the slope of this, which is the velocity. And the slope of that is the following. So first thing I have to do is take the slope of this, which is just simply omega. And the slope of this is just a constant. And so I'm not even really looking at that as a slope. So it's going to be a times omega, because that was the slope of this. And then I have to take the slope of cosine, and the slope of cosine is negative sine, and it's still the sine of the same thing here. So that is the velocity. Okay, now I want to find the acceleration. So acceleration is the slope of velocity time graph. So I'm going to do the exact same thing again. So acceleration is, well, the slope of this, oops, sorry, I'll pull it down a little bit. The slope of this is just omega, and this again is just a constant out here. So now it's going to be negative a omega squared, and now the slope of cosine, or excuse me, of sine is cosine. So it's going to be cosine of omega t plus phi. So there's the acceleration. Okay, now we're supposed to draw a force diagram for this thing here. So the force diagram would look like the following, because it says it's been released. So we pulled it back and we released it. So I hope that you see that there's only going to be one force causing a net force, and that'd be the force from the spring. Yeah, there's going to be a weight force, but that doesn't affect the motion. There is going to be a normal force, and that doesn't affect the motion either. There's no friction, so we don't have to worry about that. So there's our force diagram. All right, so now I'm going to write a net force equation for this, and the net force would be equal to negative kx. Okay, so far that looks pretty good. Now F net is equal to MA, so I'm going to plug that in as well. MA equals negative kx. And let's solve that for acceleration. A equals negative k over m times x. And so there's our answer. Number 5, derive an expression for the period of oscillation. All right, so acceleration is really the second derivative of the position. So I need to think, in other words, it's like this. D, no, I always mess this up. dt squared, d squared, there we go. I have to think of something when I take the slope of it twice, I get the same function again, except I get a negative. Well, it's only sine and cosine that do that. So I'm going to go ahead and plug this in for the acceleration right here, and I get negative a omega squared cosine omega t plus phi equals, and then I'm going to plug in negative k m, and I'm going to plug in for x this function up here. So a cosine omega t plus phi. So the a's cancel, the negatives cancel, the cosine omega t's cancel. I'm left with omega squared equals k over m. I need to find the period of oscillation. So this is kind of like they call it the angular frequency. I like to think of it as kind of an angular speed a little bit, since we're kind of doing that stuff with kinematics. And it goes through 2 pi radians in a time period of 1 period. So in other words, omega is equal to 2 pi radians in 1 period of t. So I'm going to plug that in here, and I get 4 pi squared over t squared equals k over m. And if I solve this for t, I get the following. T squared equals 4 pi squared m over k. So there we go. If the spring is stretched twice as far, how will that affect the period, the maximum velocity, and the maximum acceleration? Well, realize that the maximum velocity, let me come back up here, Vmax. I don't think we were asked to find that, but anyway, Vmax. Realize that Vmax would be this part right out here, because sine of whatever only varies between 1 and -1. That's it. So Vmax is going to be negative a omega. And acceleration max is kind of the same thing. It's negative a omega squared. So you can see here that the amplitude does, which is, we're talking about how far it stretches, that's the amplitude, right? And that's how far we're stretching it. That has no effect on the period. So none. No effect. For the maximum speed, if you pull it back twice as far, it's going to be twice as fast. 2 times faster. And the acceleration, if you pull it back twice as far, it's going to have twice the acceleration. 2 times. All right. Okay. All right. All right. So for this, there is a force that's pulling this down. And it's kind of going through this arc length here. All right. So there is a torque on this, and that torque is going to be given by mg h times the sine of the angle, whatever that angle is there, sine of theta. And if we're assuming these are small angles because it says slightly, sine of theta is approximately the same thing as theta. So torque equals mgh. The torque is also given as I alpha. Oops, mgh theta, I forgot to put theta there, sorry. I alpha, which is mgh theta. Now, this is a restoring torque, so I'm going to come back up here and put a negative for all of these. It's trying to pull it back toward equilibrium. So solving this for alpha, I get negative mgh over I times theta. Alpha is really the second derivative with respect to time of theta. Well, there's only 2 functions that kind of exhibit this when I take the second derivative of it. I get the same function except negative, and that's sine or cosine. So I'm going to plug this in for theta, and I'm going to plug this in for alpha, and I get the following: negative a omega squared cosine omega t plus phi equals negative mgh over I a cosine of omega t plus phi. The negatives go away, the a goes away, the cosine omega t goes away, and I'm left with omega squared equals mgh over I. Remember, this is like an angular speed. It goes through 2 pi radians in a time period of 1 period. So it's going to be 4 pi squared over t squared equals mgh over I. And we can go ahead and solve this then for t, because we're trying to derive an expression for the period. Well, first of all, for this one, we still have to assume that this theta is small, okay, because it has to be, I think it has to be less than like 15 degrees. So this is very small, maybe 1 degree, and this is like now tripled that, okay. So if we're making the angle bigger, what we're talking about is the amplitude is getting bigger. Well, that has no effect, none, no effect. But it will, I can't spell. But it does have an effect on the velocity and the acceleration, because the velocity is related to the amplitude, and so is the acceleration. They're both directly related to the amplitude, so they're both going to be tripled. The maximum will, anyway. All right, this last one, or I guess there's 2 here. This is a torsion pendulum that kind of twists back and forth like this, okay? And it's telling us what the torque is. So I'm going to set that equal to I alpha. So I alpha equals negative k theta. That means d squared theta dt squared is equal to negative k over I theta. And again, I'm going to be plugging these 2 in. I'm going to go a little bit faster this time. I end up getting omega squared is equal to k I. When I do all the canceling and substitution and canceling. And remember that omega is like an angular speed. Oops. It's like an angular speed, so that would be 4 pi squared over t squared equals k over I. And you can solve that for t. All right, so the torsion pendulum, so now we're going to twist it so that it's only 1/2 of the twist before. Again, no effect. But it will have an effect on the velocity and the acceleration because the amplitude has been halved. So these are going to be halved